sort algorithm. Actually, the heap sort based on cheat data structure is being called min heap and max heap. I mean, actually, they used it as a data structure, and then also that's a cheat data structure. You say it's not the linear data structure; it's that non-linear data structure. We learned from the previous lesson. We already some kind of come out this fundamentals of Heapsort. At that time, you mentioned that Heapsort one of the application of the using heap data structure. I mean, let's say a heap. In order to learn Heapsort, you have to know chi, especially binary chi. Inside binary chi, you need to use complete chi. That's the things used to create min heap or max heap, and then that's a fundamental knowledge in order to use heap sort, right? That's one. As I said before, we have a many sort algorithm. You know, heap sort, quick sort, merge sort, insertion sort, bubble sort, and then bubble sort. I think you already learned in the first course in the PP1. At that time, you trying to learn what's the algorithm it is. Try it first. What's the look like the algorithm? What's the sort algorithm? But at that time, probably uh, you didn't know that one is the worst algorithm because this is the time complexity quadratic time. Bubble sort is why it exists because it's easier to programming, easier to learn. So after that you learn, you can able to compare with the other data structure. So that's the reason we learned bubble sort. But others, some sort we learned is not because of the same as efficiency as bubble sort, because better than that. So, for example, Quicksort and MergeSort, Heapsort, it's always best choice for us. They give us n login time complexity. That's really interested. That's the most efficient, I mean, most stable. Actually, in the theoretical, MergeSort is what are the best case, what are the worst case, what are the average case, always stable n login time. But unfortunately, in theoretical, the Quicksort is um, worst case is quadratic time, but average case and then best case is mostly same as merge sort n login time. But in practice, later on we also talk about in practice. The sort actually um, actually merge sort, I mean quick sort better than quick sort, as you can see. I mean quick sort, it is quick as blue, you can say quick sort is give a better performance than merge sort. And then heap sort is a little bit third, I mean third place, but it's would say quick sort is always the best. But in the theoretical way, so it means, I mean, that's one of the very important article. Actually, Stanford University, they give us, I mean, so that's we reference, that's give a very good conclusion that um, quick sort is best. But in theoretical, actually is the merge sort is more stable because whatever the each case, I mean average case or um, best case or worst case, always in login time. But quick, but the problem is, so that's kind of in the theoretical we can compare with that. But quick sort is we can try to avoid worst case, then probably we can get this better result. All right. So let's introduce the first. We need to introduce Heapsort because this is important, and then we are going to introduce the Quicksort and MergeSort. Actually, this is, it's the course is not. Will be also beginning to include MergeSort. probably because why putting together? Because of this article, right? Because of this article, I'm trying to merge together because we can able to compare with that. So that's the reason we are going to also include MergeSort, compare with the three algorithm, give a right way to look at in your mind which one is better choice. Okay, then we same time along the way we are going to introduce a little bit C++ code as well as other, if you're interested, quickly describe it if you need. Also same time I will give you several important reference, then you can able to learn in the future. Okay, let's go to the go dive first. Of course, always because we mentioned the sort, right? And then first question, you know, as we also mentioned that the three of them is the most, you know, the most important, the most fast sort algorithm. There is no existed better than those three algorithms. As you can say, MergeSort, Quicksort, Heapsort. I mean, so probably wondering how much fast sort algorithm you should be memorize a little bit, visualize your mind, so it would be better. So first of all, we just do a little bit calculation. Let's say 2 power of 6, it's 64. 2 power of 7, 128. I mean, assume that you have 100 element, right? Assume that you have 100 element, how much you can sort it. Hold on, it's not 100. I mean, let's say you have a 10 element, then the 10 element, in order to sort 10 element, based on the algorithm performance, as I say, whatever the Quicksort, MergeSort, and later on we also introduced, but nevertheless, those are performances and login time. I mean, let's say, just type it. Always the three of them is always n log in time. Okay, so it is a two-based n log in time. So let me just, how can I change the format? Can I change the format? Right. Actually, it's two-based login time. So what does means, right? So it's important that we can apply with the three of them. So let me just okay, let's say that should be belong to not only one, it belong to everyone. Okay, that's fine. That's fine. You say that the three of them has a, let's say, a measurement. Let's see. Yeah. I think I'm not. Okay, so measurements and login time. So what does means is, for example, let's say 10 element, then what will be results? 10 elements should be 10 element sorted, okay, sorted, whatever, the three algorithm, 10 multiply log to base 10, right? What do you get? Can you tell me what do you get? So 10 is 10, right? What's the 10 of the login? That's the reason I'm calculated. If it's 2 power of 6 is 64, 2 power of 7 is already out of the 108. So it means this login to base 10 means in between the 6 and 7. So it's kind of in between 6 and 7, which is 6 point something, right? for example, an average, let's say an average, this one, how can I say average? There should be, let's say, okay, this is average, right? Average should be 6 point something x6. I don't know. So it's more than 6, right? So it means they will be, if I'm saying that, let's say a 6.4, I don't know, maybe but 6.5, but basically, so that's the reason multiply 65, right? That's if I sorted 10 element, I have to sort, I have to spend 64 times comparison or computation, right? So that's if I am taking the 10 element. So if I'm taking the 100 elements, should be like us around more than 65 at least. I mean more than 350 times for only for sorting, right? Only for sorting. Still we didn't search yet, right? And then if I'm for example, in order to usually, what we human perspective expect that we want to find, right? We want to find something. We want to find minimal risk. We want to find maximum profit. We want to find something quick, right? So what you should do, actually be interested search, not sort. But if you remember, in order to get better, quicker search result, there is a one search algorithm, which is that binary search, which is login time, right? So let's say in general, let's say I want to find something. First, I needed to sort, right? Best sort plus use binary search, because binary search is better one. So find something. My goal is find something, right? Best sort. I want to use best sort algorithm, which is that three of the one of them. I can use MergeSort, I can use Quicksort, I can use Heapsort. That's the best algorithm because always the login time performance and login time performance. So what I'm doing is how much what I spend. Find something, how much I spend, right? How much I spend, right? So that's my interesting point. How much I spend, how much humans spend, how much I expect to wait for them. So that's the reason if I'm using best sort, after that sort, I can use better result. Otherwise, I can, without sorting, I can use linear search, right? So wondering which one is the better solution. Do you understand what's the problem? I have a linear search. If I'm using linear search, for example, let's say a 10 element, right? If I'm using the linear search, let's compare the two cases. I'm find something use linear search. Second case, I'm find something with binary search. And the binary search, they have precondition. I have to use sort algorithm. Otherwise, I cannot use it binary search. But linear search, we don't need any precondition, so I can directly apply it. So if I'm using 100 element, I will be only sort 60 approximately. Oh, that's a good letter. That's I'm using that one's approximately. Okay, so I'm using 650 times only for sort. After that, I'm going to login of the 100, right? What's login of the 100? I mean, login of the 6 is 6 point something, right? 6 point something. What's login of 100? I mean, hold on a second. Hold on. It's not the 10. I mean, oh, hold on a second. I'm using not this one. I mean, 6.5 is, I'm saying the 100, not 10. I mean, this 100 element. If I'm find, right, I'm wrong. That should be 100. If I'm using 10, 10 of the 2, 10 of the 2 power, right. Yeah. Actually, I'm using 100. If I'm using 10, meaningless, because 2 power of 3 is 16, right? It's less than 2. So I'm using 10 elements, meaningless. I actually it's 100 element. 100 element of the 2 power is 6, an average 6.5. That should be 100. So it means, I mean, I'm trying to sort 100 elements, sorted 100 multiply of the 100. I mean, 100 multiply 2.6. It should be 200. That's the result. What I try to calculate only for sorting 206, right? Right. So, but if I'm using the search algorithm, I just only need 99 times. This already find the worst case. I will be used 99 times to find it. But I want to use the sort algorithm already used 100 times. Then login time 100 is 6. So it means, oh, right. So that's not good, right? So if I'm using the worst, I'm not using the sort of the worst case of the Quicksort. I mean that should be Quicksort, right? Quicksort. But if I'm using sort of the let's say best case of Quicksort, maybe average. So at that time, average is 100, and 100 multiply 650, right? So 650, so it would be 65,000 times. Oh, hold on. No. Did I? 65. No. Something wrong. No, quick average. Yeah, right. Login time. No. It's login time. 6.5. 6.5. Right? It means they will be 1 0. 6,050. Average case 6,050. For finding, not sort. Finding. I mean, finding is n login time, right? So it means average case of n login is 65. So as you can say, if I'm 100 element, I find any element I needed 99 times. But if I'm using the any Quicksort algorithm, and login times already 6,050 100 times. I mean, which one is better in that case? No. It is average case of n, no, n login times. Huh? Did you understand? I'm trying to formalize the problem, right? I'm just extremely the take this one step is that if 100 element. Okay, let me quick. So if I'm using 100 element, trying to find one element, at maximum linear search will be 99 times. If I'm using the binary search, I mean binary search, finding binary searches and I mean quicksort algorithm, quicksort in login time, right? That's in login time. So it is n is 100, login is n. Oh no, hold on, not like this. 650, right? 6050. So that's only the not finding it. But if I'm finding it, means I will be use binary search. What's binary search is I will be use login time. Login time. So it means in the outside outside should be login time. Login time, 2-bit login time. Can I take this one? Okay. Right. So it's n is 2-bit login time. N should be inside of them. So it should be that like this. So what would be the result? No, hold on. Oh, no. Oh, hold on. No, it should be, yeah, I'm a little bit, no. Actually, that's correct. 100. That one plus Quicksort. Right, now it's fine. So it means, do you understand? So that's binary search, finding element after that sort, quick. Okay, that should be good. So I'm trying to finding with the binary search. Why I need a binary? Because the most fast search algorithm. So if I'm using finding binary sort, I need to quick sort. I mean, average case is better. N login time. N login time is 100. I mean, login is 100 of login is 60. Let's say 65 plus 650. So it means approximately, let's say 606, right? Approximately. I don't care how much exactly, but approximately that's 606. So I'm trying to find, it's no difference. Most time I'm using sort, but less time I'm trying to find, because I'm trying to at maximum the 100 element, 60 100 element, I will be use 6 times, I will be fine. So in average total cost is, that's total cost. Total cost, it means how much I spend, right? Total cost is 660, or average 660 times, right? So that's 99 times. Which one is better? Of course, to be very clear, I don't need to sort algorithm. I don't need the binary search. I have to use linear search. Okay. So wondering why we need to sort, right? Why we need to binary search. Okay, that's interesting. But if I'm taking a little bit bigger data set, let's say 1 million element, right? 1 million element, trying to find the linear search, but worst cases approximately 1 million times, right? But if I'm using the binary search, 1 million element should be 20 times. But I want to first be sorted, but sorted will be very too costing, right? Sorted 1 million element should be very costing. Let's say, let me just calculate that what's the 1 million element being calculated. 1 million element. After that, 30, right? 1 million element, sort, okay. Let me just say sort would be n login time, right? So I mean, I'm taking the best sort algorithm. N is 1 million, right? And then login is 20, right? Do you understand, right? So it'd be, I mean, just theoretically, n log n login, right? I mean, two-based login. Where is two-based login? That's central. Right. So at that time, it should be 20 million times. 21, 3, 20 million times for only sorting. You understood? Only sorting. After that, plus finding element, finding, I mean, total cost for finding will be 20 million times plus 20. So in approximately it's same, right? No problem. 20 million 20 times. It's same 20 million. I mean, I can just ignore the 20 because compared to that. So at that time, 1 million finding linear search is 20. But let's say if I'm frequently used, so if your data set is frequently reused, I just want to, so first time I'm going to sort is very costing, but after that I sort it, I will be get very quick, 20 million, right? 1 million will be 20 times. So 20 million is just much more than that, right? And then 1 billion elements 30 times, right? So it means if I'm using frequently reuse, then that should be, I will be, if I'm trying to use second time, third time, I will be get benefit. But in the first time, I will be very costing. So linear search is, if you just want to test it, linear search is, it should be very obvious, linear searches. But if my data source frequently reused, then should be good. Then after that, what I would do 1,000,000 times, but linear search second time still is a 1,000,000 times. Third time is also 1,000,000 times. But my second times of if I'm using sort algorithm, the second time is 20 times. Third time is also 20 times. So you understand what's the what's the cost, right? In average. So do you understand the problem? Right? Do you understand the problem?
Yeah.
Guys, are you asleep?
Yes. Yes. Yeah. Yes.
You understand the problem, right? So the problem is, so if I'm just using one times, it's not wise. wise way to apply the sort algorithm. You don't need to use binary search. But if I frequently reused, then binary search very useful. But the sorting is very cost, right? As you can see, million elements is 20 million, 100 elements is 650 times. Of course, finding is no costing, but sorting is very costing. But so that's the reason, if you're trying to, just for testing one times, this is meaningless. But you need to think about your problem is if you frequently used, so at that time you will be get benefit, right? Okay, that's if you understand the problem, then you can able to think differently. Okay, you will be change your mind. Okay, that's useful. All right. Now, second, if you understand the problem, then you understand what's the sort algorithm useful, right? So you also need to, there's at last you have to know a little bit categorize or type of the sort. There's a bad algorithm quadratic time. I mean, n square time. It's a quadratic time complexity of the sort algorithm, bubble sort, insertion sort, selection sort, and shell sort. Those are belong to bad sort algorithm. But best one is the Heapsort, MergeSort, Quicksort. So as I said, bubble sort because of very easier to programming. That's we learned the first. And search and selection sort, I'm not sure. There should be able to, and then another different kind of situation they can able to can be improved selection sort and but nevertheless it's not good as Heapsort. Those are best one. So, all right. So that's the reason we needed to interested those three algorithms, right? As you can see, n logging times, approximately those are same. But actually, as a result, we also later on compare with another article in the Stanford articles. But let's start from the Heapsort, right? But you understand Heapsort, MergeSort, Quicksort is in the performance perspective same. But first question is, what's a Heapsort? How's it created? And then how's building it? How to program it? That should be his first question. So let's start from the Heapsort. Heapsort is based on the heap, and then heap is based on the binary tree, and then inside the binary tree they have a thing called complete binary tree. What's a complete binary tree actually is the tree, the children is only two children, and then or no children, and then always try to locate it, try to place the children from left to right. Okay, so in another word, leaf level, except the leaf level, all level, except above the leaf level, always has, always, it would be perfect tree. What's a perfect tree? They has a perfectly two children. That's very, exactly balanced. The tree being called perfect tree. Then leaf level of the tree is they will be start from the left first, then and the last element should be try to from they will be position the lift from the left to right. All right, so that's a complete tree. So in order to understand the heap, first we should know that's not linear data structure. It is a binary tree, tree data structure. So it is then inside, and the Heapsort, especially they using the complete binary tree. Then you also understand, you should know what's the complete binary tree. If you remember, last lesson actually we a little bit described what's the complete binary tree, because this is a kind of necessary knowledge for heap. And then there is a two heap. One is max heap, another mean heap. Depend on your situation, we can take the max heap, or for example, if I'm trying to find maximum profit, I can take the max heap. I'm trying to find minimum risk, I can take the mean heap as a data structure. But nevertheless, there the Heapsort is they using the Heapify process also will be important, because when they delete or insert the situation, they will be broken the heap data structure. What that means is they not been positioned max heap, or they already not the max heap or min heap. So that's the reason they will be needed to process that being called heapify. They will be make sure the self balance, right? They will be make it max heap is finally tried, I mean, Heapify actually did trying to find, extract maximum value, put this in the road. In the end, that process being called Heapify. We also introduced last time. Let's just talk about a little bit Heapsort and with the those article, right? I mean, basically, I think you already understand what's a complete tree. You can able to, you can able to convert from the complete tree, but I mean, linear structure. I mean, you can convert from the tree structure to linear structure. It would be useful to your thinking, right? Yeah, because we first learned. We first learned which one? We first learned uh, array, right? So we're trying to, and then in memory management style, I mean, there's only the two data structure existed. One is the linked list, one is the array. Then that would be better data structure stored element. Then the tree can be convert to linear data structure, then you can easier to understand. Okay, that should be linear. I mean, that would be, I would say, tree data structure and linear data structure become the linear structure. I mean, that's can be convertible, but we will be using just trying to visualize from the conceptual perspective, right? So that would be good. We can store it in the array or linked list, no problem. Even more complicated, we can still can do it, but yeah. Heapsort actually said that they will be used complete binary tree. We also talked about what's the mean heap or max heap. Complete binary tree is always put, as can you say 5, 6, 1. There's a right child, left one is not there. There is, as you can see, that's a complete binary tree. That's a complete binary tree. Left from left to right. They trying to organize from left to right. Put the left first, right? That's a max heap. That's a mean heap. There's no problem. Exactly the same thing. Heapify is they trying to, for example, they try. I mean, this one, if you try, that's max heap. But if I broken it, the second scenario is if there's 7, they will be changed. Swap it, right? Compared it. Finally, they become the 7 is become the max heap. So that's kind of heapify process. If you're more complicated, I mean, you can do the same things. The heapify process can do it the same things. Now this is also, as you can see, if this is 1, it's 2, 10. It's not the max heap. So how you can make the max heap? I mean, they trying to find compare with that's the bigger one, so they will be exchange it. After that, the small one, they will be recursively say they found it, there is existed another one is bigger than that, so they will be swap it. Then still there's 6, 9, 10. Right. Right. So that's finally they become max heap. As you can see, this is a small one. The sub tree also needed to, process the heapify process. Finally, that's a 10. Each level one by one from left to right. So that's max heap. Building max heap. Building max heap. I mean, interesting that you can try to make it as a linear data structure. This is the array, as you can see. So, for example, from 1 to 10. I mean, we can you can learn from the this. Here we can convert from the non-linear data structure. Linear data structure would be useful to we can apply in the programming, right? So as you can see here, they trying to introduce what's Heapify look like. Actually, the Heapify make it this the whole process. As you can see, finally, that's become the min heap, the max heap, right? So that's but that's the first steps. You needed to have on nonlinear data structure, which is we were trying to use min heap and max heap, right? Now, but that's only data structure. But how we can create a heap sort, right? Heap sort, if we use such max heap property, large system stored in the root node, remove the root element. I mean, swap is remove the root element and put in the end. I mean, using the process that trying to sort this whole set of the element. I mean, if you trying, this is just trying to convert the max heap. I mean, that's a final result, right? 0, 12, 1, 10. I mean, it's not been sorted. So max heap, min heap is still not the way to we can get the result, but we can use the data structure to follow this process. We can sort it. So first of all, we need the swap process. What the swap is? Remove the root. Okay, remove the root. Put this in the end of the array, nth position. Okay, just remove it. Okay, because it's maximum value. Put this in the end of the array. Okay. Put this in the last element in the tree, of course, because you're trying to put this in the last one. Swap is, I mean, 9 to 10, just swap it. They're trying to going to remove it to put this in the linear data structure. Okay, that's second is remove the reduce the size of the heap by 1. I mean, because this is already useless, so you just need to remove it. So they just left the 1, 2, 3, 4, 5 element. Next step is keep heapify. What does heapify? Make this extract this maximum value, make it max heap. This become the max heap. Then continue this next step. Remove the 10th element. I mean swap element. I mean swap for. I mean this last element to 10, and then put this 10 to last element. Then remove the 10. So you just keep reducing the binary tree, but increasing the replacement of the array. Then finally they become been sorted. So as you can see, that's the final result 1, 5, 6 times. So this is actually they're using the Heapsort algorithm, so they can able to follow this process. Then okay, so interesting, right? So we can become we already able to convert the non-linear data structure to linear data structure because we can able to easier to programming it, but same time we can able to sort it. So it's interesting. So also it's very easy. So how does it look like in the coding style. It's a kind of pseudocode, but let's say we all familiar with C++. Let's see what's the C++. They trying to use namespace, whatever. All right. We know what's a Heapify. Heapify is extract. Heapify is. Do you know who know the what's a Heapify? Heapify is recursive process. They trying to retrieve the they retrieve the max heap or min heap value. Or in other words, Heapify is can make sure that the data structure is heap data structure. So it means even you just destroy it, they will be keep balance itself. So it will be get better performance. So that's Heapify. As you can see, so that's we introduced last time. I mean, left, right. They trying to, if its left side is smaller than that, then we need to swap it. But this is another case. Yeah. But there is one more things in the Heapsort swap, right? Then also Heapify. And then Heapsort, these swaps actually they going to, swap. There should be swap, right? Swap. The swap function actually used it in standard library, so that should be fine. Actually, the exchange the pointer of the position, that should be fine. Yeah, that's for Heapified. Or they become the heap data structure, and then this is becoming the. I'm just remove it. Put this in the array. At the first, this is empty, but in the end, the heap, after that you go through in this process, they becoming the, they fulfill the array is being sorted. So interesting, right? So, but from we interested how's look time complex, right? So best sort algorithm and logging time, worst sort algorithm and logging time average look like very stable. One more thing is that space complexity is fixed time. That's very interesting. But compared to other algorithms, they will be spent, I think it's or n times. But Heapsort is very efficient. So you will be save time. If you're trying to save space, Heapsort is, best one. From the theoretical part, that's exactly same with the MergeSort and the Quicksort, except the Quicksort of the worst case. And then at that time, they will be used in login time, but this is a fixed time. So this is an interesting part. Right. So I think that should be one interesting article. You can see it in the future. If you're trying to learn better, that's a Heapsort, right? What I can say. So Heapsort, first of all, you should understand heap data structure. Non-linear data structure. You should understand how the max heap or min heap can be typified, keep self-balanced. That's interesting that we can use it in the Heapsort. And the Heapsort is actually, there is a Heapsort algorithm. They will be introduced that the processes, swap it with the root to end last node, then remove it. But that before the remove, you need to put this in the array last element. Then what they're doing actually using the same data structure. That's the previous one that when they remove it, they just don't allow it to operate that set. So that's the reason they just used only the one array. That's the reason fixed time. That's the reason this one is, even they didn't copy the any space. They just used the same space. So that's the reason fixed time. So that's swap, then remove it, and the heapify. Heapifies root elements. So again, that heapify that the root element gain the highest element at the root, the process repeat until the item in the last has been solved. So that's for five process, how's Heapsort working? Actually, the sort and the heapify, that's very interesting. From I think it's one picture worth 1,000 words. In order to understand, that should be very interesting picture too. You can understand this algorithm. I think you understand it right now, right? That's a Heapsort. Now next things that Quicksort. How's a Quicksort algorithm? Quicksort, as you can see, Quicksort actually best case is n log n time, average case n log n time, same as Heapsort, but one thing's worst case is quadratic time. It's scary. It's scaring me. But space complexity, all log n time. As you can see, this one a little bit not better than Heapsort, but Heapsort is better than that one, right? So, okay, that's look like from the performance time sort complexity perspective. But next thing is how's Quicksort working, or how they can actually programming. So actually the process is divide control approach, the same as MergeSort. We will be explained later on, but they have one term being called pivot. They will be used the pivot. If you take the pivot is position where any position in the data set. You can take from the left side, you can take from the right side, even you can take from in the middle. If you take from the middle, it should be same as MergeSort, but you can take any place. So that's the reason if I'm trying to sort it, then if this element's already been sorted, then I'm trying to put it in the end. So at that time you will be get worse algorithm. So pivot position is very important. If you take the better pivot position, you can avoid worst case. Okay, let's see how is Quicksort created. Quicksort, let's say the pivot element start from the left side. Then what you're doing is they try to put the smallest element in the left side, biggest element in the right side. Then the left side has always been sorted, so they will be concentrated. Another time, they again same algorithm. They put this in pivot position, the 6 always, and then you beginning to do the same things. 6 is pivot position, then they do it again. They do it in the smallest element in the left side, biggest element in the right side. So the same thing, swapping finally, 1 to 3. Here's the place. Hold on a second, there's a 2's been already. If you take the 6, I swapped it with 6, and then at the first there's those are the bigger one, and then this is still not been compared. They will be compared. If there is bigger one, they will be keep it as it is. If it's smaller one, they will be put this in the sorted position. So as you can see, those are, and then 6, 7, 6, those are already bigger than that, so they don't change any position. But it's one is a smaller than 2, so they will be at the time you can find it. you can swap it the small element with the biggest element in this here. So they will be swap it. Keep that way. Keep that way to they doing these things. They will be beginning to swap it. Now second is 6 is as a last element, because there's already been small element we already discovered. And then I mean 2 is of course small element. Now they beginning to change the pivot position with the 6, so they will be repeat the same things. After that, they will be, each of them, they will be concurrent with the merge process. I mean, those are, for example, there is the pivot element, again, the choice of right side element, and step and second repeat the same things. I mean, that one, if it's 2 is a pivot, then after that 6 is pivot, then after that 8 is pivot, then finally they've been sorted. That's the idea of the Quicksort algorithm. So at the first, we trying to position itself this right side is pivot position. I mean, as long as the 2 is smallest one and pivot, they put this in the left side as smallest element, right as biggest element. Then they will be beginning to, based on that, they will be exchange the pivot position, then keep do the same thing. And here's a 6 pivot, and then they trying to put this in small element. There is no any small element here, so that's it. But after that, the left is 3 elements, 8 is pivot. Then they will be use it as again. So they will be just one times comparison. They can able to be sorted, or 7, 8, 9. Then after that, they will be just merge it together, put it together, then becoming the sorted element. So that's Quicksort look like. Let's see how's I mean, there's I think this is pseudocode. There should be Quicksort partition. I mean, there's a 2 element. One is a partition, another is a Quicksort style. How's the algorithm, right? There's a 2 important steps. It's, as I said, partition is you're trying to find minimum value and the maximum value. Then I mean pivot value, if is let's say highest value is pivot value, then you put this in the smallest value in the right side of the pivot, biggest element put in the left side. No, sorry, smallest element in the left side, biggest element from the right side. They will be finally been arranged. They will be swapped. Then one part will be been sorted. Then they will be then second time they change the pivot position based on you found it the unsorted part. They try to find the highest element as well. So they will be take it the partition as a recursive process, then take this sort algorithm, repeat it, same things, then yeah, they become dependent. They become being sorted. I mean, that's a important aspect. They've been called pivot position, right? If you understand pivot position, is MergeSort also very same. MergeSort also very similar. That divide conquer idea. I mean, yeah. So that's usually in order to understand the heap, order to understand algorithm data structure, first when you look at this picture, you should be, if you read this picture, then after that, easier to understand the source code. Don't directly go to the read source code, then you might be, have a problem of understanding. Maybe you spend too much time, sometimes confusing. So this last comparison, that's interesting, right? That's worst case. Another things you need to avoid. so you need to, by conclusion, that you try to worst case, try to avoid worst case. We try to avoid worst case, then Quicksort is best one, better one. All right. So that's a Quicksort. So Quicksort, how it's been implemented, how it's look like the problem. Then in that point, space complexity is not good as Heapsort. All right. Quicksort algorithm, worst case is that one. Depend on your pivot position is if you avoid pivot position is worst cases can be avoided. So some especially in the practice, Quicksort is always can be predictable. I mean, been proved that Quicksort can be get better performance because they can able to predict this, avoid bad pivot position. Okay, last one's MergeSort. MergeSort is another very stable, theoretically, always, n login time, as you can see, average case, worst case, best case, always the same, so it's more stable. But in the articles they say MergeSort is actually behind Quicksort. So MergeSort in second, third is Heapsort. All right. So how's MergeSort? Next question: how's MergeSort is being created? Assume that this is a data source, didn't been sorted. What they're doing is actually they will be divided to part. I mean, in the middle. Then each of them is keep divide. Finally, they will be been. After that, each of them just left it one. They will be swap it. For example, 5 and divide. For example, in this stage, 6, 5, and 12. This is each of the individual, and then they trying to put this in the small segment in the left side. Then they just compare 2 times 6 and 5, then been sorted. So we don't need to compare 6 to 12 because they already compared just 2 times. So that's interesting that save time just 1 times. Then other sub tree is same. Now as you can see, 10, 9, 1, they will be compared to smallest one. I mean this 10 is small. I mean you can, as you can see, 10 is bigger one, so they will be compared to the bigger element. They will be put this in the upper side of position. Then after that you already been sorted. You just need to merge it because this already been sorted. Just so that's the reason MergeSort. In the final step, they will be merged. All right. So let's see how's MergeSort been created. Right. So that's an article. You can reference it. So actually, they will be divided 2 parts. Then the third part's been becoming the merge process. So that's it. Algorithm, as you can say, first you need to find the middle element, right? In the end, each of the, so they will be, after that you can compare it. Then finally they will be merged. It's very easy to understand. First, as you can see, let's start from the while. And here's let me, there should be C++ code. Do you need C++ code? All right, here's C++. Good. So as you can see, there is a they actually, this is array itself. P and Q and R, which is that. Hello? Any question? So actually, I mean, if you not, if you think this is boring, I mean, that should be, we can able to, you can able to check it in later. You just run it itself. Even you can say different kind of language of programming, but nevertheless, that's first you need to figure out how does it look like. I mean, at the end, each of these should be comparable. As you can say, that's a binary data structure. As you can see, they will be divided always. At the first, you just find in the middle, then divide it to subtree, subarray, then they will be divided again. Finally, there is no element can be divided, then after that beginning to compare. If you already been sorted, then beginning to merge it. So as you can see, that's one sub, that is another sub, then finally they become the merged, then been sorted. So merge sort. Time complexity is, as you can say, very stable, very stable. Space complexity is worse than Quicksort. And the best one is, of course, Heapsort. Second one is Quicksort. Third one is MergeSort. All right. So that's another another comparison. But nevertheless, there is one article, Stanford University. They provide one article. They written by PhD student. Actually, gave us the very good graph, which is that always in the practice, as long as become, I mean, the data sources, when they more than 10,000, they becoming the differentiated the performance. Less than 1,000, there is no difference. But after that 10,000, 10,000 still in the Heapsort and the MergeSort, no difference. But when they 20, I mean, maybe around 30,000, we can able to differentiate it in the Heapsort and the MergeSort. But they already becoming the differentiated at the 5,000. I mean, 5,000 Quicksort already extraordinary performance show up. Quicksort, that's the reason Quicksort is always best. I mean, as long as as you can say, there's a, this is 1 minute, right? No, yeah, 100, the position that, very clear, Quicksort is best one, MergeSort is second one, Heapsort is third one, right? There's also another article, a worst case of the bubble sort, insertion sort, selection sort. At the time is shell sort is better one, selection. I mean, insertion sort second one, selection third position, bubble sort is worst, bad one. I mean, so that's another things that you can compare in the same quadratic time complex data structure. You can learn from the article. Very good article. All right, there is a reference if you are. Okay, so that's by the conclusion we learned the three algorithm. Then also as a conclusion that this article is very important to visualize in your mind, keep this concept in the future, which is very useful, right? I think that's I'm end of the lesson. This is my lesson for today. I hope you have a question.
I